Let us start with one of the new topic in our chapter, that is heating effect of electric current. Students, you already learned this topic earlier, but let us learn this topic in the form of equations. Let me show you that how the energy is transformed into heat energy. Let us take a day-to-day life example in which you are using fans and any other devices at your home. Whenever you switch on fan to maintain the current, the source which is providing energy to the fan has to provide some energy to maintain the current through that device, from which part of energy is used to rotate the blades of the fans. Otherwise, the other part of energy is expended in the form of heat, which raises the temperature of the device. So let us say heat energy. We will study one topic in the form of Joules heat with some equations. Let us watch one video to understand heating effect of electric current.
Heating effects of electric current. Let us understand the heating effect of an electric current in this video. We know that the battery or a cell is a source of electrical energy. The chemical reaction within the cell generates the potential difference between its two terminals that sets electron in motion to flow the current through an resistor or a system of resistors connected to the battery. In order to maintain the current, the source has to keep expanding its energy. However, a part of this source energy in maintaining the current may be consumed into useful works like in rotating the blades of an electric fan. The rest of the source energy may be expanded in heat to raise the temperature of the gadget. We often observe this in our daily lives. For example, an electric fan becomes warm if used continuously for a long time. On the other hand, if the electric circuit is purely resistive, that is, a configuration of resistors only connected to a battery, the source energy continually gets dissipated entirely in the form of heat. This is known as the heating effect of an electric current. This effect is utilized in devices such as electric heater, electric iron, and electric toasters and others. Consider a current I flowing through a resistor of resistance R with a potential difference across it V. Let T be the time during which the charge Q flows across. The work done moving the charge Q through a potential difference V is VQ. Therefore, the source must supply energy equal to VQ in time t. Hence, the power input to the circuit by the source is P is equal to V into Q by T is equal to VI, or the energy supplied to the circuit by the source in time t is P into T or VI into T. This energy expended by the source gets dissipated in the resistor as heat. Thus, for a steady current I, the amount H produced in time t is H is equal to VIT. Applying Ohm's law, that is, V is equal to IR, to this equation, we get H is equal to I square into RT. This is known as Joules Law of Heating. The law implies that the heat produced in a resistor is directly proportional to the square of the current for a given resistance, directly proportional to the resistance for a given current, and directly proportional to the time for which the current flows through the resistor. In practical situations, when an electric appliance is connected to a non-voltage source, the equation representing the Joules law of heating is used after calculating the current through it by using the equation I is equal to VR.
I am drawing one common circuit here in which this is a device. Let us say this is a device which is connected with a source. Let us say this source is battery or something which is providing potential difference to this device. The equation for potential difference is work done per unit charge. So to maintain the current, work done will be equal to VQ by the source. So W will be equal to V into Q is the work done by the source. So at last I can say that VQ is the energy which is provided by the source to this device. If we want to calculate the power input by the source, power will be equal to work done per unit time. Here we concluded that VQ is the energy provided. Then V into Q upon T will be equal to the input power. So if I say I was equal to Q by T, that we know current, I can write the equation P will be equal to V, Q by T represents I. This is the input power as per potential difference and electric current. So we can say that energy expended by the source is actually dissipated in the form of heat energy. So here we are going to calculate that heat energy, and for that I am going to write one equation of heat energy. Here heat energy can be mentioned by the symbol H. As we know, power is equal to work upon time. Work will be equal to power into time. This was the energy provided by the source. Now as we know that equation of power is equal to work upon time, we can also calculate work is stored in the form of energy also, or work done can be in the form of energy. So energy will be equal to power into time. So as per the power input equation, power input is equal to V into I. So instead of power and instead of energy I am writing heat energy, which is dissipated, VIT. This is the equation for heat energy dissipation. Let us understand Joules' law of heating as per the equation of dissipation of heat. The dissipation of heat can be written as H is equal to VIT. Now as per Ohm's law, V is equal to IR. I am substituting the value of V here, and it will be equal to VIR into IT. Now here I is same, so I multiplied by I will become I square RT. This is the equation for Joules' law of heating, where we can consider that heat is directly proportional to the square of the current. Heat is directly proportional to the resistance through which current I is passing, and it is also proportional for the time through which current is passing through the resistor. So students, this is the equation for Joules' law of heating. We will study next about the application of Joules' law of heating. Thank you.